My name is Jawad Hajjahya and I'll present our work FlexWatts. In recent years, there is a hot debate in industry and academia on power delivery networks. PDN issues are becoming even worse as process technology scales down. First, I will give a high-level overview of the talk. Client processors typically use one of three commonly used power delivery network architectures: motherboard voltage regulators, integrated voltage regulators, and low-drop output voltage regulators. The energy efficiency of each of the three PDNs varies with processor power and workload characteristics. Our goal is to provide high energy efficiency and high performance PDN architecture by leveraging the advantage of each one of the three PDN architecture across the processor wide range of power consumption and workloads. To this end, we propose FlexWatts, a new hybrid adaptive PDN for client processors that introduces three mechanisms. First, new hybrid voltage regulators that are allocated for processor domain with a wide power consumption range that dynamically switches between two modes, IVR mode and LDO mode. Secondly, static allocation of off-chip VRs which have high energy efficiency for low and narrow power range for the rest of the domains. And finally, a novel algorithm that switches the hybrid PDN to the mode that is the most beneficial based on processor power and workload characteristics. We evaluate FlexWatts using our new architectural PDN model, PDN Spot. FlexWatts improve the average performance of spec CPU 2006 and 3D Mark workloads by 22 and 25% respectively for 4-watt thermal design power system. And FlexWatts reduces the average power consumption of video playback workload by 11% across all tested TDPs. Here is the outline of the talk today. I will begin with a brief overview on client processor PDN architectures. The power delivery network is the electrical system that provides supply voltage to the processor's domains. A PDN consists of a power supply, voltage regulators, network of interconnections, decoupling capacitors, and power gates. There are three different commonly used PDNs. PDNs normally use switching voltage regulators and or low-drop output voltage regulators. An SVR can be placed into motherboard, which is called MPVR, or integrated on-chip, which is known as IVR. The PDNs perform differently based on processor power and workload characteristics. MPVR and LDO PDNs are more energy efficient at low thermal design power and light workloads compared to IVR. IVR PDN is more energy efficient at high TDP and heavy workloads than LDO and MPVR. MPVR is more energy efficient than LDO in graphics workloads. We conclude that a single PDN architecture cannot provide high energy efficiency across a wide power consumption range and a wide variety of workloads. I will now discuss the motivation and the goal of our work. We evaluate the potential benefits of the three PDNs, IVR, MPVR, and LDO across different TDPs, application ratios, and workloads. Application ratio is the switching rate of a component for a workload when compared to the highest possible power. We use our validated model, PDN Spot, to validate the efficiency of the three PDNs. We use the metric end-to-end power conversion efficiency, or end-to-end efficiency in short. End-to-end efficiency of a PDN is the ratio between total output power consumption to total input power consumption of the PDN. We use multiple workload traces from spec CPU 2006, 3D Mark, and video playback workloads. Our first observation is about TDP effect on PDN's efficiency. When executing CPU and graphics-intensive workloads with different application ratios, we observe that IVR PDN has lower end-to-end efficiency at the 4-watt TDP compared to MPVR and LDO PDNs. And we observe that IVR PDN has a higher end-to-end efficiency at 50-watt TDP compared to MPVR and LDO PDN. End-to-end efficiency crossover point at which the IVR end-to-end efficiency becomes higher than the MPVR and LDO end-to-end efficiency exists at some TDP between 4-watt and 50-watt. We conclude that a TDP affects the end-to-end efficiency of a PDN. At low TDP, the MPVR and LDO PDNs are more efficient. At high TDP, the IVR PDN is more efficient. Our second observation is about the workload effect on PDN's efficiency. Workload's application ratio and workload type affects the PDN end-to-end efficiency. The end-to-end efficiencies of MPVR and LDO PDNs increases with application ratio due to load line effect. Different workload types had different end-to-end efficiency curves. For example, the LDO end-to-end efficiency is higher than MPVR end-to-end efficiency for CPU-intensive workloads, but is lower than MPVR end-to-end efficiency for graphics-intensive workloads. LDO efficiency is more dominant in graphics workloads due to the high voltage difference between core and graphics domains. We conclude that application ratio and workload type have significant effect on PDN's end-to-end efficiency. MPVR and LDO PDNs have lower end-to-end efficiency with lower application ratio. LDO PDN has lower end-to-end efficiency on graphics workloads. Our last observation is about the power state effect on PDN's efficiency. The end-to-end efficiency of IVR PDN is lower than that of MPVR and LDO PDNs for computation-light workloads and low power states across all TDPs. A video playback workload spends 10% and 90% of its execution time in light workload and low power states respectively. MPVR and LDO PDNs have 12 and 11% average power consumption respectively than the IVR PDN due to higher end-to-end efficiency of MPVR and LDO PDNs. We conclude that the IVR PDN is energy inefficient in computational light workloads. This negatively impacts energy consumption and battery life. Based on our three key observations, we conclude that there is no single PDN for modern client processors that provide high end-to-end efficiency across all TDPs, workload types, and application ratios. Our goal is to provide a PDN architecture that provides high energy efficiency across the wide range of power consumption and variety of workloads. Now, I will explain the technique to achieve our goal. We propose FlexWatts. FlexWatts is a new hybrid adaptive PDN that provides high end-to-end efficiency for the wide power consumption range and workload diversity of client processors. FlexWatts is based on three key ideas. First, new hybrid voltage regulators that are allocated for processor domains with wide power consumption range that dynamically switch between two modes, IVR mode and LDO mode, to maintain high energy efficiency across the wide range. Secondly, static allocation of off-chip VRs which have high energy efficiency for low and narrow power range for the rest of the domains. And finally, a novel prediction algorithm that switches the hybrid PDN to the mode that is most beneficial based on processor power and workload characteristics. FlexWatts has three components. A hybrid adaptive PDN that includes hybrid VRs and off-chip VRs. A voltage noise-free mode switching that transitions the hybrid PDN between two modes, IVR mode and LDO mode. A new mode prediction algorithm that automatically determines which PDN mode would be the most beneficial based on system and workload characteristics. Now I will talk about each component in more detail. The first component is a hybrid adaptive PDN. FlexWatts PDN consists of two components. Off-chip VR are located to each system domain with a low and narrow power consumption range. Hybrid VRs are located to system domains with a wide power consumption. The hybrid PDN can dynamically switch between two modes, IVR mode and LDO mode, based on the expected end-to-end efficiency benefits of each mode for the current workload and power consumption. The hybrid PDN shares multiple die, package, and board resources. The second component is a voltage noise-free mode switching mechanism. FlexWatts performs mode switching using three steps, while the compute domains are idle to prevent any voltage noise. First, we place the processor in idle power state for a short period of time. Secondly, we configure the hybrid PDN and update the on-chip and off-chip VR levels. And finally, we exit the idle power state and resume the processor with the new PDN mode. The final component is a runtime mode prediction algorithm. A new runtime prediction algorithm predicts which PDN mode among the two modes, IVR mode and LDO mode, provides the best end-to-end power conversion efficiency. The end-to-end power conversion efficiency is a function of the application ratio and the workload type, the TDP and the power state of the system. We store two sets of end-to-end efficiency curves inside the power management unit firmware. One set for IVR PDN and other set for the LDO PDN. The PMU firmware estimates each of the input parameters at runtime. I will next present our evaluation of FlexWatts. First, I will present our methodology. We evaluate the PDNs using our new open-sourced PDN spot model. We evaluate FlexWatts with 3 classes of workloads. For CPU, we use spec CPU 2006 benchmarks. For graphics, we use 3D Mark benchmarks. And for battery life, we use web browsing, light gaming, video conferencing, and video playback benchmarks. We compare FlexWatts to the 3 commonly used PDNs of client processors. Let me start with showing the results for the CPU workloads. At TDPs lower than 18 watts, FlexWatts provide up to 22% higher performance over the IVR PDN by operating mainly in LDO mode. At TDPs higher than 18 watts, FlexWatts provides up to 7% and 4% higher performance over MPVR and LDO PDNs by operating in IVR mode. FlexWatts significantly improves CPU performance compared to IVR at low TDPs by operating in LDO mode. FlexWatts provides higher CPU performance compared to MPVR and LDO at high TDPs by operating in IVR mode. Now let us see the results for the graphics workloads. At TDPs lower than 25 watts, FlexWatts provide up to 25% higher performance over IVR PDN by operating mainly in LDO mode. At TDPs higher than 25 watts, FlexWatts provides up to 3% and 6% higher performance over MPVR and LDO PDNs by operating mainly in IVR mode. At TDPs lower than 25 watts, FlexWatts perform slightly worse than MPVR and LDO PDNs due to the higher load line of FlexWatts, the large difference in operating voltage across the cores, LLC, graphics domains. We conclude that FlexWatts significantly improves graphics performance compared to IVR at low TDPs by operating in LDO mode. FlexWatts provides higher graphics performance compared to MPVR and LDO at high TDPs by operating in IVR mode. Now I will present the results for battery life workloads. Battery life workloads have a fixed performance requirement. They consume the same power for all TDPs. FlexWatts reduces the average power consumption between 8% and 11% on battery life workloads compared to IVR PDN. FlexWatts consumes up to 1% more power than MPVR PDN. We conclude that FlexWatts is almost as energy efficient as both MPVR and LDO, and up to 11% more energy efficient than IVR. We have other results in the paper. For example, FlexWatts board area and bill of materials compared to other PDNs. FlexWatts has comparable BOM cost and board area to IVR PDN. FlexWatts PDN has significantly lower BOM cost and board area compared to MPVR and LDO PDNs. Comparison to PDN used in Intel Skylake X processors that combines IVR and MPVR PDNs. Intel Skylake X PDN provides higher performance and lower energy consumption than IVR PDN. FlexWatts provides significantly higher performance and lower energy consumption than the Intel Skylake X PDN. Let me quickly conclude my talk. Client processors typically use one of 3 commonly used power delivery architectures: MPVR, IVR, and LDO. The energy efficiency of each of the 3 PDNs varies with processor power and workload characteristics. Our goal is to provide high energy efficiency and high performance PDN architecture by leveraging the advantage of each one of the 3 PDN architectures across the processor's wide range of power consumption and workloads. To this end, we propose FlexWatts, a new hybrid adaptive PDN for client processors that introduces 3 mechanisms. First, new hybrid voltage regulators that are located for power domains with wide power consumption range that dynamically switch between 2 modes, IVR mode and LDO mode. Secondly, static allocation of off-GVRs which have high energy efficiency for low and narrow power range for the rest of the domains. And finally, a novel prediction algorithm that switches the hybrid PDN to the mode that is most beneficial based on processor power and workload characteristics. We evaluate FlexWatts using our new architectural PDN model, PDN spot. FlexWatts improves the average performance of spec CPU 2006 and 3D Mark workloads by 22% and 25% respectively for 4-watt thermal design power system. and FlexWatts reduces the average power consumption of video playback workloads by 11% across all tested TDPs. Thanks for your attention. For many more details, I invite you to read our Micro 2020 paper.